Good day, everyone. Hybrid simulation lets us model complex real-world scenarios by combining different techniques. From smarter cities to more secure elections, it's transforming how we solve problems. Today, we'll explore its impact and potential.
Hybrid simulation is a modeling technique that combines two or more types of simulation methods, such as discrete event simulation, system dynamics, and agent-based simulation, to better represent complex systems. By integrating different simulation approaches, hybrid simulation enhances accuracy, flexibility, and efficiency in analyzing real-world problems. So why it is important? This approach enhances decision-making by allowing researchers, engineers, and policymakers to analyze interactions between different components of a system, predict outcomes, and test solutions in a controlled virtual environment. Hybrid simulation is widely used in fields where single simulation techniques fall short.
These are the 5 real-world examples of hybrid simulation that we're going to present to you. So what are we waiting for? Let's start. The first real-world example is cybersecurity attack and defense. Agent-based for cyber attacks and continuous simulation for real-time network traffic monitoring. Prepared by Ian Kirby A. Reyes. Why hybrid simulation in cybersecurity? Cyber threats are evolving rapidly, and traditional security testing is often reactive. Hybrid simulation allows us to mimic real-world attacks in a controlled environment, leading to better threat analysis and response strategies. Agent-based simulation models individual entities, such as attackers, defenders, and network nodes, as agents with specific behaviors. Each agent follows a set of rules, mimicking real-world cyber attackers like hackers, malware, or bots. This helps analyze attack strategies and system vulnerabilities. Continuous simulation monitors real-time changes in network traffic, system performance, and security events. It detects anomalies, identifies attack patterns, and measures the effectiveness of defensive mechanisms. This is widely used in intrusion detection systems, IDS, and real-time security analytics. How hybrid simulation works. Step 1. The agent-based simulation models cyber threats, such as phishing, DDoS, and malware. Step 2. The continuous simulation tracks network activity in real time. Step 3. The result is a more effective and adaptive cybersecurity strategy, where defense mechanisms are continuously tested and adjusted based on attack simulations and live data monitoring. Real-world applications. Hybrid simulation is applied in various cybersecurity domains, including cybersecurity training to simulate attacks and train IT security teams, intrusion detection system, IDS, testing to evaluate how well an IDS detects threats, incident response planning to prepare for cyber attacks with real-world scenarios, zero-day threat analysis to predict new threats before they occur. Key benefits of hybrid simulation in cybersecurity. Hybrid simulation offers several advantages. More realistic cyber attack modeling, improved threat detection and response, continuous adaptation to new attack patterns, cost-effective compared to real-world breach testing, enhances security resilience over time. In conclusion, hybrid simulation is revolutionizing cybersecurity by enabling more effective threat detection and response. By combining agent-based and continuous simulation, organizations can proactively defend against evolving cyber threats. Next, we'll discuss the hybrid simulation of IoT-based smart homes, prepared by Raifil Sean V. This section will explore how hybrid simulation improves the performance, security, and efficiency of smart homes. A smart home is a residence equipped with IoT devices that automate tasks like lighting, security, and energy management. A hybrid simulation approach combines different modeling techniques to predict device interactions, power consumption, and security risks before real-world implementation. AI enhances this by learning from data and making real-time adjustments, improving energy efficiency, security, and user convenience. Hybrid simulation is essential for smart homes due to the complexity of IoT interactions. It simulates how devices like sensors, cameras, and thermostats work together. It predicts power usage, reduces costs, and enhances sustainability. Security testing helps identify vulnerabilities and prevent cyber threats. Performance analysis tests device responses under different conditions, and cost reduction strategies lower energy expenses. Hybrid simulation combines three approaches for accurate predictions. Discrete event simulation, DE, models individual device actions, such as turning on and off lights. Agent-based modeling, ABM, simulates how users interact with smart devices. System dynamics, SD, analyzes long-term energy trends and system performance. AI plays a key role in smart home simulations. Predictive maintenance detects early signs of device failure and alerts the user. Adaptive automation adjusts device settings based on user habits. AI enhances security by detecting unusual activity and triggering alerts. Real-time optimization adjusts HVAC, lighting, and appliances based on environmental changes. Data analysis helps identify usage patterns and suggest improvements. An example of AI-powered smart home energy optimization addresses the problem of high energy consumption caused by inefficient device usage. The hybrid simulation models energy consumption and analyzes usage patterns to improve efficiency. AI tracks appliance usage and adjusts settings in real time, predicts peak energy demand, and schedules devices accordingly. It also simulates power failures and suggests backup solutions. The impact includes lower electricity costs, reduced energy waste, and improved device longevity. As we've learned, hybrid simulations combine different technologies to model complex systems. Let's dive into a practical application, the hybrid blockchain-based voting system.
Blockchain voting is a promising solution for secure and transparent elections. But why hybrid blockchain? It combines the security of private blockchains for voter authentication with the transparency of public blockchains for vote tallying. This ensures both privacy and trust in the system. Here's how it works. First, voters register, and their identities are verified on a private blockchain. When they cast their votes, encryption ensures security, and the vote is recorded on a public blockchain for transparency. Automated verification prevents tampering, ensuring a fair election process.
A real-world example is Votes, a mobile voting app used in U.S. elections, especially for overseas military personnel. Voters authenticated their identity through biometrics, cast their vote via smartphone, and the blockchain secured each transaction. While Votes showed promise, it also sparked debates about security and public trust, highlighting the need for further innovation. Hybrid blockchain voting faces key challenges. Security risks like hacking and privacy breaches remain a concern. Scalability is another hurdle, especially in large-scale elections. Plus, there are legal and regulatory barriers that slow adoption. But the future holds promise. AI-powered fraud detection can enhance security. Decentralized identity verification will strengthen authentication. And as trust grows, we move closer to a more transparent and secure voting process. The road ahead isn't easy, but the potential is game-changing. Today, we will discuss how hybrid simulations, combining agent-based and continuous simulation, can enhance disaster preparedness, response efficiency, and recovery planning. These simulations help us better understand both human behavior and environmental changes during disasters, allowing for more effective decision-making. Let's begin. So for our key points. First is, what is disaster simulation? It is the process of using computational models to predict, analyze, and improve responses to disasters. Why is it important? Helps in preparedness by optimizing evacuation, resource allocation, and recovery planning. Why hybrid simulation? Agent-based simulation, ABS, models individual decisions and movements. Lastly is, continuous simulation, CS, tracks environmental changes over time, flood levels, fires, etc.
So, how does it work? These simulations model different disaster scenarios, like earthquakes, floods, or pandemics, and analyze key factors such as resource allocation, evacuation routes, and communication strategies. By predicting outcomes, teams can optimize their response plans ahead of time.
One major application of hybrid simulation is evacuation planning. ABS helps predict how people behave during an evacuation. Some may panic, others may take alternative routes, while CS monitors hazards like flood levels or fire spread. For example, organizations like FEMA use these simulations to design evacuation routes and optimize emergency plans, ensuring people reach safety efficiently during disasters. Effective resource distribution is critical during disasters. Hybrid simulations assist by using ABS to track human decision-making in shelters, hospitals, and logistics teams, while CS monitors real-time supply levels of food, medicine, and fuel. AI-powered systems optimize distribution routes, preventing shortages and ensuring aid reaches those in need. The World Health Organization, WHO, has used similar AI-driven systems to distribute medical supplies efficiently during crises. Hybrid simulations offer several advantages, including improved accuracy in disaster predictions, better resource management, and AI-powered decision-making. By combining human behavior modeling with environmental tracking, emergency planners can design better evacuation routes, allocate resources efficiently, and react to disasters faster. This ultimately leads to reduced casualties and improved disaster response effectiveness. In summary, hybrid simulations provide a powerful tool for disaster preparedness by modeling both human actions and environmental changes. AI further enhances these simulations by enabling real-time data analysis, predictive modeling, and optimized response strategies. In the future, advancements in IoT sensors, AI analytics, and real-time disaster monitoring will make emergency response even more effective, helping save more lives.
Welcome to the Urban Flooding and Drainage System Simulation. This topic is designed to analyze, predict, and visualize flood risks in urban areas, helping to create more resilient and efficient drainage solutions. Let us now delve into the introduction. In rapidly growing cities, urban flooding poses a major challenge. Effective drainage systems are essential, but designing them requires precise forecasting. Through simulation, we can model flood scenarios, assess risks, and enhance drainage strategies to minimize damage. This process enables engineers to develop smarter, more efficient solutions before they are applied in real-world situations. Now, let's discuss why simulating urban flooding is essential. Through simulation, we can accurately predict flood risks by analyzing how stormwater flows in urban areas, helping us identify flood-prone zones before disasters occur. Additionally, simulations allow us to optimize drainage systems, ensuring they are designed to handle extreme rainfall effectively. Most importantly, this technology enables us to test different drainage solutions in storm scenarios virtually, eliminating the need for costly and time-consuming physical trials. By leveraging simulations, we can develop smarter, more resilient flood management strategies for our cities. Now, let's look at the key elements of urban flooding simulation. Hydraulic models simulate water movement in drainage systems. Together, these elements enhance flood prediction and management. GIS mapping identifies flood-prone areas for better planning. Scenario testing helps optimize flood defenses by simulating different storm conditions. Why is urban flooding simulation needed? Cities are becoming more vulnerable to flooding due to several factors. Impervious surfaces, such as roads and buildings, prevent water absorption. Overloaded drainage systems struggle to handle extreme rainfall, especially when outdated or poorly designed. Climate change brings more intense and unpredictable weather patterns. Simulation helps us understand these challenges and design better drainage solutions before real damage occurs.
That concludes our presentation. Thank you so much for your time and attention. I'm Xander Abian, and I'd like to introduce my group mates who helped make this presentation possible.
I am Akab Zoran.
I am Gonzalez Ryfield.
I am Lapasaran Janine Lorraine.
And I am Reyes Ian. Thank you.